Okay, so let's go ahead and go over today's examples. So today's examples, we're going to be simplifying radicals first. So before we start simplifying radicals, here's a few things that I think you should know. You should know the perfect cubics, the perfect quartics, and the perfect quintics to help you simplify the radicals. So let me show you the first, the perfect cubics that you need to know. You need to be able to, either memorize them or recognize them or just, write them down when you're simplifying these. But the perfect cubics will be 1 because 1 cubed is 1, 8 because 2 raised to the third power is 8, 27 because 3 cubed is 27, 64 because 4 cubed is 64, 125 because 5 raised to the third power is 125, and then the last cubic that you need to recognize is 216, which is 6 cubed. So to simplify these, it would be helpful if you write those down. So those are called the perfect cubics. Then we're also going to be simplifying like the fourth root. So those are called quartics. So let me just write it out. It's called perfect quartics. I'm just going to write down quartics here. So the perfect quartics that you need to be able to recognize are 1, because 1 to the fourth is 1. 2 to the fourth is 16. 3 to the fourth is 81. And then the last quartic you should probably recognize is 4 to the fourth, so 256. Usually, I don't think I'll ask like that big, but definitely 81, 16, and 1 you need to be able to recognize. And then finally, I think the last one that we should probably just know are the perfect quintics. So when you do the fifth root, so the perfect quintics. And let's put them, I guess let's put them here. Quintics. So for the fifth power, I usually only ask, well, 1 is always a perfect everything, but 1 and then 2 to the fifth power, so that'll be 32. Those are usually the only ones I'll ask. So 2 to the fifth power, you need to recognize that as 32. Okay, so now that we have the perfect cubics, quartics, and quintics, here's how I start simplifying my radicals. So let's start with number 1. We're going to simplify the cube root. So we need to look for this perfect cubics. To simplify the cube root of a number like 54 here, you need to figure out which perfect cubic goes into 54. Or in other words, what's the biggest perfect cubic that can divide evenly into 54? So I'm going to rewrite this as, instead of rewriting it as 54, that's going to be 27 times 2. Because 27 times 2 is 54. And then the rest is just going to stay the same. X to the 6th, y to the 10th, and z to the 17th. Okay, so like I was saying, to simplify the cube root of 54, I broke it down into the cube root of 27 times 2, and now you should be able to simplify the cube root of 27. The cube root of 27, since it's a perfect cubed, that's just 3. The cube root of 2 cannot be simplified, so we're going to leave it as the cube root of 2. But let me scoot it over on this side over here. The order really doesn't matter how you write it, but I always like to write like my radicals at the very end, and then everything that's outside of a radical I like to put here first. So I took out the 3 outside of the radical because the cube root of 27 is 3. The cube root of 2, I just left it as the cube root of 2. And now when it comes to the exponents, those are easy. To do the cube root of the exponents, you just have to divide those exponents by 3. Or in other words, how many times does 3 go into 6? So that would be 2 times. 3 times 2 is 6. No remainder. So I'll leave it like that. Okay, now here, when you divide 10 divided by 3, that's not a perfect number. So 3 won't go into 10 perfectly. 3 goes into 10 3 whole times with a remainder of 1. So here's how you write that. You write y to the third, because like I said, 3 goes into 10 3 whole times. 3 times 3 is 9. But there's a remainder of 1. So the remainder of 1, you're going to put it inside of the radical. And if it's a 1 like that, you don't have to put the 1, but I'll just put it there to explain it to you. So let's try it again with the exponents. So 17, you need to see how many times 3 goes into 17 and see what the remainder would be. So 3 goes into 17 5 whole times. So I'm going to write down 0 to the 5th on the outside because 5 whole times. But 3 goes into 17 5 whole times, but there's a remainder of 3 times 5 is 15, so that means there's a remainder of 2, because from 15 to 17 you're missing 2. So then I'm going to write that remainder of 2 as z squared on the inside. And that's how I simplify cube roots. You need to make sure you practice simplifying these. Let's try example 4. First, let me pause for questions. That's not what okay, so example 4. I'll do the same thing I did with example 2. I'll do the same thing I did with example 1. This time we're doing the 4th root, so we need to look at the quartic. We need to be able to see which quartic will divide this 162. And sometimes it's hard to see it like that, so instead let me do it as, if I know that 162 is even, I'm going to divide it by 2. That could help, and then I'll see what's left over. So 2 goes into 162, 81? 2 times 81 is 162, yeah. And now 81 is a quartic, so you have to recognize that one. X to the negative 8, y to the 12, e to the 23rd. Okay, so let's repeat the process. The 4th root of 2, there isn't a 4th root of 2, so let's just leave it as the 4th root of 2, and I like to put it at the end. The 4th root of 81, that is the perfect 4th root or perfect quartic, so that would be 3. And now again for the exponents, you just have to take your exponent and divide it by this index root. So if I have x to the negative 8 divided by 4 is negative 2. One thing about exponents is that you're not supposed to leave negative exponents. So if you do have a negative exponent like here, negative 8 divided by 4, that would be x to the negative 2. Instead of putting x to the negative 2, you want to put the variable x on the denominator with a positive 2. So that's how you change a negative exponent to a positive exponent, by moving it to the denominator. So now I have over x to the positive 2. Keep going with the y. 4 goes into 12 3 whole times with no remainder. I'm going to put it on the top because it wasn't negative. And then finally z. 4 goes into 23 5 whole times, because 4 times 5 is 20, and the remainder would be 3. So z cubed. And now that's how I simplify something like example 2. Because if you don't have any questions, we can just keep going. But our next unit is this. You're just going to be simplifying radicals. So maybe I do have some questions. I'll pause. Alright, so one thing I forgot about example 2, and it's called the even odd rule, and that's because example 2, you're taking the even root, like the 4th root. So number 1, we did not need the even odd rule because I was doing the cube root, which is not an even root. So anyway, so example 4, you are taking an even root, and then if any of your variables had an even power, such as x to the negative 8 and y to the 12. And finally, if your answer came out to be odd, then you do need to put absolute values. So here, the only ones that might need absolute values are the x and the y, because those have even powers. Z won't need absolute values no matter what, because z is raised to an odd power. So let's check out the x and the y. So here they are. X will not need the absolute values because the final answer is also raised to an even power, so it doesn't fall into the even odd. However, the y will need the absolute values because this is what's called the even odd rule. You started with the 4th root, which is even, of an even power, like 12, and you ended up with an odd power like 3. So that's even, odd. So thank you. That was number 2. So now let's try number 3. Number.
I have a question.
Yes, question. All right, number 3. This one will not need the even, odd rule at all because these are cube roots, which are not even roots. So the way I would do that one, since they're both just a cube root and a cube root, we can just combine them into one single cube root. So I'm going to go ahead and combine these by multiplying them together. So 10 times 4 is 40. Y to the negative 4 times y to the negative 2. I guess you have to remember your rules of exponents. But when you multiply variables, you have to add the exponents. So that would be y to the negative 6. And then x to the negative 3 is just there. So now you start applying the cube root. So the cube root of 40, you look at the perfect cubics and you see which perfect cubic will go into 40. So I'm guessing 8 goes into 40. So that's what I'm going to read. I'm going to rewrite 40 as 8 times 5. 8 times 5 is 40. And then the rest stays the same. And now I can go ahead and simplify by doing the cube root of 8 is just 2. So put 2. The cube root of 5, there isn't a cube root of 5, so let's leave it as the cube root of 5 here. I don't think this is going to come out good. Actually, let me put the 2 right there. And then, because those exponents are going to be negative. Y to the negative 6, you just divide the negative 6 by 3, so that's y to the negative 2. But remember, to make it positive, just put it on the bottom as y squared. And same thing with the x. X to the negative 3 divided by 3 is going to be negative 1. But instead of putting x to the negative 1, you can just put x to the first on the denominator. The order doesn't matter of the variables, but number 3, that would be my final answer. 2 cube root of 5 divided by xy squared. And that's why our first quiz is going to be on Delta Math. Yeah, because you're going to have to type those up. It's easier in Delta Math. And you will practice for the quiz by doing that little review activity in Delta Math. But that's numbers 1, 2, and 3. And I guess the next few examples here, I'm going to show you, the purpose of these are to show you how to rationalize denominators. So number 4. Number 4 has a radical or a fourth root on the denominator, and you can't leave radicals on the denominators. You have to rationalize them. So let me see. The best way to explain how to rationalize denominators, I guess you need to understand how you rationalize square roots, I guess. So let me start with that first. I guess right here. Okay, so most of you guys already know how to rationalize the square root of x. And the way you would rationalize the square root of x is just by multiplying the numerator and the denominator, or by the square root of x. Or in other words, multiply by square root of x over the square root of x. But I guess you need to understand why. And that's because, for starters, a square root has a little invisible 2 there. And the reason why we multiply by just another square root of x is because if you do multiply the square root of x times the square root of x, this becomes like an x squared. And now when you take the square root of x squared, or in other words, when you divide 2 by 2, you end up with just x to the first power, and it's good to go. But now, now we need to simplify it. Let's pretend that was just 1 over the fourth root of x. Okay, so here it goes. So ignore the 2 for a minute. So now let's try to rationalize 1 over the fourth root of x. So the most common mistakes that kids do on these, they want to rationalize this the same way they did with the square root. I think they want to do like the fourth root of x over the fourth root of x. But let me show you, like, that's not going to be right. This will not help you rationalize, because if you only multiply by the fourth root of x, here's what you end up having on the denominator. The fourth root of x times the fourth root of x is only the fourth root of x squared. And 4 won't go into that 2 at all. Like, you can't simplify that any further. That's not going to get rid of this fourth root. So you're gonna have to think about like what do we need to do to rationalize this, and the goal is to make this become a 4 here, because if you do have the 4th root of x to the 4th, that's going to become x with no radical anymore, because 4 goes into 4 one time. So now we just need to adjust this here. In order for this to become the 4th root of x to the 4th, here you're going to have to multiply by not just the 4th root of x, but by the 4th root of x cubed. And the reason why is because if I do multiply the 4th root of x cubed times the 4th root of x, that becomes the 4th root of x to the 4th, because you're supposed to add the exponents, like x to the 3rd times x to the 1st becomes x to the 4th. And that's how you rationalize denominators like that. So we're going to try the same thing again with number 4 here. If I want to rationalize, so this was just all extra. I didn't even finish it, but that's okay. Okay, so if I wanted to rationalize number 1, here's what I'm going to multiply by. I'm going to multiply by the 4th root. Okay. So here, this is 2 to the 1st power. So I'm going to multiply by 2 to the 3rd power, because that's going to make a perfect quartic of 2 to the 4th power. Same thing with the x, like I just explained. Since this is x, then I'm going to multiply by x to the 3rd power over x to the 3rd power. And now here's what my final answer will be. I guess I'll just put it over here. Okay, so on the numerator, I have the 4th root. Since I'm multiplying by 1, then it's just the 4th root of 2 to the 3rd is 8 x cubed. And on the denominator, let me show my work right here. On the denominator, it ends up being the 4th root of 2 to the 4th, x to the 4th. Because when you, like I just said, when you multiply 2 to the 3rd times 2 to the 1st, that becomes basically 16, so 2 to the 4th. And x cubed times x to the 1st becomes x to the 4th. And now I can actually apply the 4th root. So 2 to the 4th is 16, so that is a perfect quartic. So that's just regular 2. And then the 4th root of x to the 4th, that's just regular x. And that's the final answer on number 4. So now I'm going to pause the video and I'm going to let you practice rationalizing something like number 5a and 5b. Those will be, you have to rationalize a perfect cubic or cube root, and then you have to rationalize here a perfect quintic, the 5th root. So I'm going to pause the video. So number 5, you were supposed to rationalize the 1 over the cube root of, I should probably erase some of this so I have room here. Okay, so number 5. I ran out of white out. The way you rationalize 1 over the cube root of 4 x squared. Okay, I guess the first thing I did was, you don't have to do it this way, but to make it the most simplest way possible, I went ahead and I wrote 4 as 2 squared because that's 4. So now if I did want to rationalize it the way I have it here, then I'm going to multiply by the cube root of, if I already have a 2 squared, I only need to multiply by 2. And if I already have an x squared, I only need to multiply by x. So the cube root of 2x. And that's because if I do that, my numerator would just be the cube root of 2x. My denominator here, I'll just show you my work, but my denominator would be 2 squared times 2, that's 8. Which the cube root of 8 is a perfect cube. Or you can write it as 2 to the 3rd power if you like. X squared times x is x to the 3rd power. So final answer for number 5 should be this. It should be the cube root of 2x all over 2x. Because the cube root of 8 is 2 and the cube root of x cubed is x. And that would be your final answer for number 5a. Okay, let's try 5b. Again, on this one, before I even get started with the question, because there's a 2 on the numerator and an 8 on the denominator, that can be simplified. That can just become a 1/4. So let's do that first. 1/4. So basically number 5B, you are doing rationalizing 1 over the 5th root of 2 squared x cubed y. Yeah, so number 5B, it became 1 divided by the 5th root of 4, but I always like to write it as 2 squared, times x cubed times y. So now if you do want to rationalize this, you're going to have to multiply by, I just don't have enough room. Just going to borrow it here. We're going to have to rationalize by, if you already have a 2 squared and you're trying to make a perfect quintic, you're going to have to multiply by 2 cubed. If you already have an x cubed and you're trying to make a perfect quintic, you're going to have to multiply by x squared because you want them to be exponents of 5. And next, if you have a y to the first and you want a perfect quintic, you're going to have to multiply by y to the 4th. So 2 cubed x squared y to the 4th. So then again right here, my numerator would be the cube root of 2 to the 3rd, which is 8, x squared, y to the 4th. And then the denominator, I'm not going to show my work anymore, but the denominator is going to be the cube root of 2 to the 5th, which would just be 2. The cube root of x to the 5th, which would just be x. And then the cube root of y to the 5th, which would just be y. So I skipped my work a step. And that's how you would do something like number 5. 6 and 7 are going to be similar. And I don't think we'll have time to do both. So let's skip 6 and try 7. And if we have time, we can come back. Do try to do number 6 on your own. And check with the answer key online to make sure you did it right. Let me try number 7. So number 7, there's nothing that can be simplified here because 48 and 9. Wait, can 48 go into it? Like, they can't be reduced, right? Like by 3? Yeah, it looks like it because 48 can be 16 times 3, and then 9 can be 3 times 3. So let's reduce those. So that would become a 16, and that would become a 3. 3 times 3 is 9. Yeah. So reduce your numbers if possible. Now I'm going to rewrite number 7 as the 4th root of 16 z to the 4th divided by the 4th root. When you have a fraction in a radical like that, you can just take the radical of the numerator and denominator. You can just write it separately. So the denominator would be the 4th root of 3 y cubed with an x. Okay, so now I'm ready to actually simplify. So on the numerator, 16 is a perfect quartic, so the 4th root of 16 is 2. Z here can go into Z, 4 goes into 4 once, and this one's technically supposed to have an absolute value, which I think I forgot on the answer key, because this is an even root of an even power that comes out to be odd, so that would probably need absolute, values. And then on the numerator, there's nothing we can do on the numerator. It's going to stay as is, so we're going to have to just rationalize it. So again, to rationalize roots, you need to make perfect, in this case, we need to make perfect quartics, or in other words, your exponent has to be a power of 4. So since I already have a 3 to the first here, I'm going to multiply by a 3 cubed. Since I already have a y to the cubed here, I'm going to multiply by a y to the first. And since I have an x to the first here, I'm going to multiply by x cubed. Squeeze it in here. So my final answer. On the numerator, I have a 2 absolute value of z times the 4th root of 3 cubed is 27. Y x cubed. I usually put the letters in alphabetical order, but it doesn't matter. And then on the denominator, again, the fourth root of 3 times the fourth root of 3 cubed, that becomes the fourth root of 3 to the fourth, but I'm just going to write it as 3. And then y to the third times the y to the first becomes y to the fourth, but since I take the fourth root, it's just a y. And then x cubed times x to the third is x to the fourth, but since I'm taking the fourth root, it's just x. So that's what the answer key should say. The x and the y don't need absolute values because the x and the y started as odd powers, like y to the third, x to the first. So I'll pause the video. All right, so the second lesson for today is going to be called rational exponents. Basically, rational exponents is just when you have a fractional exponent. So in other words, your exponent is a fraction. So here's what you need to know about these. I told you a little bit last unit, like when we did, remember when we did like x to the 1/3? I told you that was the cube root of x. Now I'm going to tell you like the whole thing. So anytime you have a variable raised to a fractional exponent, so raised to an exponent that's a fraction, the denominator here would become the root. So if you have to the 1/3, then you're doing the cube root. If you would have to the 1/4, then you would be doing the fourth root, and so on. However, the one you definitely need to know, like the formula, the generic formula for all fractional exponents is this one here, which is when you have a variable like a or x raised to an exponent that's a fraction, here's what happens. The denominator is still that root. So like either the square root, the cube root, or the fourth root, or something. But the numerator will now become the exponent inside of that root. So we're going to have to practice that. And finally, you should also know that in this format, if you have the nth root of a to the m power, it can also be written in this format here, which is the nth root of a parentheses to the m power. Okay, so let's just try it. Here goes. Using this formula, or using, I guess, this format, let's do number 8. I'm going to need you to write number 8 in exponential form. So exponential form means like with an exponent. And so let me just show you. So this format here is what I have here. I could rewrite that as, that's the same thing as having the fifth root of b to the third, because all I did is I'm working backwards here. So here I had the fifth root of b in parentheses raised to the third. So I rewrote it as the fifth root of b to the third. In other words, I just put the 3 inside of the root because that's possible. When you have it in this format, you can just take your exponent and put it inside of the root. And now I'm going to write it in fractional exponent. So I'm just going to take that and write that as b raised to a numerator and a denominator. So based on the formula, the exponent that's inside of the root, it's the numerator. The exponent that's on the outside of the root is the denominator. So that's my final answer on number 8. You're just going to have to practice the rule on the formula. So let's try it again. Number 9. 6 is just a whole number. That's just 6. Okay, let's do here the square root of a to the 5th. If it helps you, you do need to remember that a square root has an invisible 2 there. So again, now I'm in this middle step here. I need to rewrite the square root of a to the 5th as an exponent, as a fractional exponent. So that means I'm going to write a, and then it's going to have a numerator and a denominator. The numerator should be what's inside of the radical, so that's a 5. And then the denominator is what's outside of the radical, like the root, so it's an invisible 2. And that's my answer. Let's keep practicing one more time with these fractional exponents. Number 10. So you're going to have to apply this rule individually. So here's what I mean by apply this rule individually. I guess let's just do the fifth root of -2 first. So if I have the fifth root of -2 and I ask you to write that with a fractional exponent, that's going to be like a negative 2 raised to some exponent. Remember, the numerator should be what's inside of the root. So for this negative 2, there is an invisible 1. So that's my numerator. The denominator should be the root. So in this case, the denominator is 5. So that's part of my answer right now, negative 2 to the 1/5. So now let's keep going with the rest. Let's do the 5th root of x squared. So that's going to be x to some power. So one more time. The numerator is the exponent that's inside of the root. So 2. The denominator is just the root. So the number outside, so the root of 5. And then you can I guess we can keep going with the rest, but let me show you how you write the final answer for number 10. So for number 10, my final answer should be, okay, for sure, negative 2 to the 1/5. Next, x to the 2/5. Okay, the next I'm just going to do it in my head. Y should be y to the 1/5 because the y has an invisible 1 over 5. The denominator should always be 5 because that's the root here, so it should always be 5 for this example. And finally, z to the raised to the 3/5. And oops, that's the final answer. So you're going to have to practice writing writing fractional exponents given like the roots. So practice that. And now, I guess let's go ahead and finish the last 3 examples, and we have time. Now we have to go backwards. So for the last 3 examples, we have the fractional exponent. So we have the m over n, and now we need to write it as what's called radical form. So previously we wrote them in exponential form. So those are called exponential form. Now we're going to write in radical form. So here's how you do it backwards. Number 11. The numerator, okay, x is going to go inside the root. The numerator is the number that goes inside of the root. The denominator is the actual index root. So that's one way to write it in radical form. I could also write it as the 4th root of x to the 15th. Either one's correct. Either one's correct. However, I like to write them, it's easier to write them leave it as the 4th root of x to the 15th. So I would prefer if you leave them like that, because now the only thing you have to be careful with radical form is once you write it in radical form, make sure that it's simplified all the way. And by all the way, I mean here, like my index root of 4 can actually go into 15 3 times. 4 times 3 is 12 with the remainder. So I guess basically we were back to like the first lesson. So simplifying radicals. So again, one more time, when you change it to radical form, make sure you've completely simplified the radical. So here we go. The 4th root of x to the 15th. 4 goes into 15 3 whole times. So x to the 3rd. So 4 times 3 is 12. The remainder would be 3. So again, 4 goes into 15 3 whole times with the remainder of 3. Now that's the final answer. So let's keep practicing. Number 12. Y to the negative 3.5. For starters, change negative 3.5 to a fraction. In other words, y to the negative 7/2. So y to the negative 7/2. And next, okay, there's different ways to do it from here. I'm just going to go ahead and change my negative 7/2 to a positive 7/2 by moving my y to the denominator. There's different options you could have done. I just decided to do that. I went ahead and changed the y to the negative 7/2 and made it y to the positive 7/2 by moving my y to the denominator. Now I can do my formula. In order to write this fractional exponent as a radical, I'm going to write The numerator goes on the inside of the radical. The denominator is the index root. And that would almost be the answer. Technically, that is radical form, but then you have to simplify it. So I guess let's just keep borrowing some space here. 2 goes into 7 3 whole times with the remainder of 1. Yes. And then again, that is simplified, but then that's not the most simplified version because you're not supposed to leave radicals on the denominator. You have to rationalize them like we did up here. So this is going to be easy to rationalize because it's just the square root. So to rationalize the square root of y, you could just multiply by the square root of y over the square root of y. So number 12, final answer, is going to be the square root of y, which if it's a square root, you don't have to keep writing that 2. You can just write it as the square root of y. Over on the denominator, the square roots here would just go away and you'll have y, but then you already have a y cubed. So it's actually going to become y to the 4th. So that's my final answer for number 12. We'll pause for a question. Last example, number 13. I guess I don't have to do it over here because there's no room over there. So 13. Let's write this as a radical by using those fractional exponents. First of all, the 6 does not have a radical. So 6 doesn't have a exponent, so it's just a normal 6. I think same thing with the z. It's just a normal z. Now, the x and the y have fractional exponents, so those are going to be going into the root thing. So for the last time, let's do the 11 over 5. The numerator goes inside of the root. The denominator goes on the outside of the root. Same thing with this one, 3 over 5. The numerator goes on the inside of the root. The denominator goes on the outside. Now here, this was easy because they were both had a denominator of 5. If they don't have the same denominator, I think that's what we're going to do on Thursday. You're going to have to just change the one of the fractions to have the same denominator. So like, for example, like if this was a 10 instead, then we would have to write this as like 6 over 10. And I think that's Thursday's lesson. But 13, this looks very promising, the right answer. You always have to be very careful though at the very end. At the very end, make sure that it's simplified. And one way to check is your index root has to be make sure that it doesn't go into these, what do you call them? Into these exponents. So in other words, your index root has to be bigger than any of the exponents here. So for example, 5 is not bigger than 11, so that means that that can be simplified. So in other words, 5 goes into 11 2 whole times. So let me write that. 5 goes into 11 twice, so 2 whole times, so x squared. And then the remainder would be 1. And now 5 won't go into 3. So one more time, if your index root is bigger than the exponents on the inside, then you're good. You have simplified it all the way. But if your index root is not bigger than the exponents on the inside, then it needs to be simplified. So now that's the whole end of the lesson. Let me end the video.